rectangle Vx, would that be a good thing to do? So class, if I let the bottom of the rectangle be length x, would that be a good thing to do? You know what, let me redraw this and let me write this in red. If I let this rectangle, the base of the rectangle, and let that be x, will that be good or bad? Will that be good or bad? If I call this guy x, the length of the rectangle be x, will that be okay or not okay?
I think there will be a confusion with the
Now,
coordinate.
this will be confusion now. If you call this guy and call it x, then that will be a problem. You can call this guy a or b or whatever, but if you call this x, you note that x is already pre-existing, pre-existing variable here. So if you want to call something by x or y, it has to be consistent. Otherwise, you will get in trouble. So as soon as you call this guy x here now, your entire problem is going to blow up. It is a logical mistake. It's a systematic mistake. It's a big problem. So if you're not sure, don't use x or y. So in this case, then what is a good choice here? Can you call, how about this? Can you call this guy, can you call this point P x, y? Yeah, that is okay. If you call this guy point P and call this x, y, that is okay. What that really means is we are going to call this guy right here, this guy, just after this rectangle, this guy we are calling it x. And is that okay? Yeah, that is okay. Because this x will be consistent with this x right here. So if you want to use an existing variable, you have to be consistent. But on the last test, a lot of you made a mistake. Because on the last test, what happened was you had a question like this curve, and a curve like this. And the basic essence what you did was you call this guy x, and then you call this guy x, and you call this guy x as well. I mean, it's like this. You have a curve here, you have a curve here, and then you want to find a common tangent. You're calling this guy x, and then you're also calling this guy x as well. But they're not the same x. And so this is a systematic logical mistake, which is irrecoverable. All right? If you don't know what you're getting into, then please use different levels. All right? Otherwise, the entire problem is going to blow up. Okay, so we call that P, and so now we have this x and y, and this guy we call it y. So now what is it? It says here find the maximum area. Okay, that's the objective function right there. So the function which shows up immediately after the word maximum minimum, that is the objective function. And this is our rectangle right there. So we draw a rectangle. This is a diagram. Again, this kind of a diagram is not required. The diagram is needed to help us understand the problem. It is to help us understand the problem. Also, many times it is not going to give us the solution either. Okay? But at the end, we can check and see whether it makes sense. So diagram is good for two reasons. One is to understand the problem. Second, it will check whether the final answer makes sense. So now let's get the setup. The setup A equals 2xy. Note that we have two independent rows, x and y. And what is the relationship with x and y? Well, xy has x and y. X and y, the two numbers must satisfy this equation because this point is on the curve, y is 12x, 12 minus x. So that is, the equation itself is actually condition in this case. And then find the maximum A, there you go. And here I wrote down x is between 0, and x is bigger than 0, and y is bigger than 0. But if you want to be precise, you can actually you can say x is actually what? Between 0 and 1. Between x is less than 0 is less than x, less than 2 square root of 3. And then you can say y is actually between what? Not just bigger than 0, but also y is actually what? Less than 12. And by the way, some math teachers and some textbooks, instead of writing this with a regular inequality, they actually put an equal sign here. And if you put equal sign, that's okay too. Because on these problems here, at the end point, what happens? Nothing will happen at the end point anyway. So many math teachers and many math textbooks, they actually do put the zero, the equal sign up there, equal sign. So they put less or equal to instead of equal to. Less, okay? But anyway, in this case, the difference difference between these two is not that important anyway. Nothing happens at the endpoints, but so it doesn't really matter. So here, you can say x is greater than 0, or you can say x is greater than 0. Again, there's no penalty for these things here, because on these kind of problems here, it's not that critical. You can put it there, you can don't put it there. Either way, whatever you put is okay. But put something in there. Put some range, okay? And so a is equal to this, and then y is equal to 12 minus x squared, so we have this right here, and then that's a cubic. And how does dA dx here? Take the derivative, and then of course you take the derivative, and then you have to factor this out completely. So in chapter 3, you don't just take the derivative, you have to take the derivative factor. Okay? That's, yeah, you have to factor that. So that's that, and then now what? Factor, and then now, second derivative is not required because this is a what? Maximizing, minimizing. So we only apply the method where we only use the first derivative. So now the chart is required. Okay, this is required. So let's look at this. We have A, and then we have X, and then we have dA dx. So now let's analyze it. dA dx here. Again, the chart on optimization is very simple. There's usually not much going on, but still, let's do this anyway. The chart is still required because you have to show your work. So here at x, x runs from 0 to where? X runs from 0 to 2 square root of 3, which is square root of 12. Again, if you're not sure, then you can just put infinity here. But although nothing happens in infinity, so let me just put 2 square root of 3. So what happens here? We need a 2 here. And note that the critical value negative 2 is out of domain, so we don't need that guy. Yeah, we don't want this P to be on this side. We want to call this guy P also? No, we'll just let the P be on this part of the curve. So we will let x is between 0 and 2 square root of 3. I think that's a little easier. Okay? And then dA dx is 0. And then dA dx when x is bigger than 2 is bigger than 2 plus, and the minus here. Note that there's a minus here, and this side will be a plus. If x equals 2 is a 0 multiplied with 1. Note that there's a 1 there, that means it will cross over sign. It'll go sign. So A will go up and A will go down, and so now you can see that that's where the maximum is. Now you can say, therefore, max A equal to A when what? When x equals 2. And when x equals 2, what is the area? The area will be what? What is the area? That will be, let's see, if you put in the area, what will that be? That will be area x equals 2. So that will be 2 times 2, and then times what? Plug in 2 there, 2 squared is 4, so 12 minus 4 is 8. So it looks like that will be what? Will be 32. 32 units. It looks like there's no unit here, so that 32 will be fine. Now, class, this is the logic I'm not going to accept. Okay, class, if you do this kind of work, there will be a penalty, all right? So let me show you what that is. So I'm going to save this here, and I'm going to clear this. Class, now watch me here. If you show me this kind of work, then there will be a penalty. So what you see is that you do all this, and then dA dx is equal to what? dAd is equal to this guy right here. And then what you say is that A prime at x equals 2 is equal to what? Is equal to 2 is equal to what? Is equal to now 0. Okay, is that true? Yeah, that is true. At x equals 2, A prime is 0. And it is okay to write A prime. So you can write dA dx, or you can write A prime if you like. And as long as we understand that prime is ddx in our case. If you put ddx like this, and then evaluate at x equals 2 equal to 0, doesn't matter how you write it, so either way will be acceptable. So now this is the question here. A prime is 0. Therefore, we now write this. Therefore, max x is the answer. Therefore, max A occurs at a when x equals 2. The question is, am I going to accept this now? And then this comes out to be what? 32. So this comes out to be 2 times, this will be 2 times, and then 2 times, and that will be 8. And then you write 32. Now, if you do this here, is it correct? Yeah, it is correct. This is correct. This is correct. Correct, but not justified. The problem is this. The derivative is 0. The derivative is 0. If the derivative is 0, you get a maximum, yes or no? If the derivative is 0, do you get a maximum? What do you think? If you get a 0 here, if the derivative is 0, does that mean that you get a maximum here? Huh? Do you get a maximum? Do you get a maximum if the derivative is 0? Yes or no?
You can also get minimum.
Yeah, you can also get minimum. Or it may not be maximum. Because if a is equal to, let's say, like this, or a is equal to a cubed, if I give you, let's say, how about this? You know what? I'm not going to, let me call by a different name here. That this will go. Let's say there's a function b. Let's say function b is equal to, let's say, this is equal to x cubed. And then this x cubed here is a different function. Now, what is b prime? B prime is dv dx is equal to what? Is equal to now 3x squared. Okay, so now we have this, and now you look at this, x and b here, and then we have b prime, so b prime. So b prime here, and you can see what happens here, this, and then what happens at 0? Well, b prime is 0, but note that this guy's plus here, and so that means it's increasing. Do you get a minimum here, maximum here? No, we don't get minimum, we don't get any maximum here. So what I'm trying to say is, if you just have this right here, okay, this. Okay, so now let me let me just erase this part right here. Let me erase this part. So b prime is equal to 0. Then does that mean, can we conclude that that we have maximum b? We have what? So we have b prime. So we have b prime at 0 is equal to 0. Okay, so the question is what? The question is this. Max b is equal to b at x equals 0? Yes or no? And the answer is no. What I mean is this: correct, but not justified. Many of you, when you write your solution, this is how you argue. You tell me that it's correct. You're right. You are correct. I'm not saying it's wrong. But in this class, being correct is not enough. You have to justify. Is that clear? If you just write something correct, you just give me the right answer and you tell me it's correct. Yes, you're right. It is correct. But that's not math. Math, you have to justify. Is that clear? So you have to justify according to the rules of mathematics, according to the definition of mathematics. So that's why you have to justify. So it is not justified. It is correct, but it's not justified. Actually, in this case, yes, no. Actually, it's not justified. Actually, in this case, there's no need to justify. Because in this case, no, this is not correct. What am I saying here? You know what? No max b at x equals 0. In this case, there's no max. So what I'm saying here, if you come back to our problem A here, I mean, in this case, it is correct. So when you say max A is equal to A when A equals 2, it is correct. Yeah, it is correct, but not justified. So how do you justify? You have to give me the chart. You have to give me the chart here. And then show me it's what? It's going up and then going down. It's going up and going down? I think so. Wait, did I, alright? Wait, did I, the previous chart, did I write the answer correctly? Let me see. What was the, what was the solution before? Let me just erase everything here. I don't know how to get my previous screen. So let me just go back all the way here. Let me see what I did here. Okay, let me see what I did. Okay, so max A? Yes. Max A, right? Yeah, it is max A. Yes. Oh, yeah. I think I wrote the arrow the wrong way. It should be going up and going down. There's max. Okay, save. Okay, so I saved already, so that's clear. Okay, so now what I'm going to do is I'm going to now come back, let's go to example 4. Now, example 4, the problems are getting a little more interesting. Again, the graphs are a little more interesting. What is the graph? Here, the graph, what is the program? The problem is we have a cylindrical cans. So it looks like we are dealing with a cylinder. We're talking about a manufacturer who is making cans, who is producing cans like this. Okay? So now let's look at example 4. A company wants to manufacture cylindrical cans which will hold 125 centimeter cube. Okay, so this is the volume here. We want the volume to be what? We want the volume to be 125. 125 centimeter cube. Okay. Lateral surface area means the side surface area costs 2 cents per centimeter square. And the top and the bottom surface area, bottom surface costs 4 cents per centimeter square. So it looks like the bottom and the top are more expensive. The side is a little bit cheaper. So we are not talking about surface. So when you make cans, the cost of the can depends on the surface area, not the volume. Okay? So can I find the dimensions of each can? Dimensions, I should say dimensions of each can. Dimensions meaning, what do you mean by dimensions? What's the R and what's the H? These are called the dimensions. The dimensions could mean many things in math. But when it comes to cylinder, we talk about like the radius R and the height H. We call these guys dimensions. If you have a circle, then the radius somehow we call this a dimension. If you have a sphere, then we call radius a dimension. Okay, so dimensions could mean many things.
No, fuck
the
you.
radius and the height are dimensions. So find the radius and the height. So find the radius and the height of each can such that the cost is minimum. Now we want to minimize not the surface area, we want to find the cost. Does everyone understand what that means? We want to minimize the cost. So let's say the company gets an order, and the order is that they must make a can, they must produce cans which can hold 125 centimeter cube. But let's say the requesting company does not make any does not specify how the can should be made, how the can should be shaped. And so the manufacturing company now can decide. They can decide what kind of a can they want to make, a tall, skinny can, or do they want to make a short, a wide can? Well, they want to make a can which will minimize the cost. So that's what the question is. Okay, so in this case, what we're going to do is, let me now do this here. We have a can. Let me call this guy here, this. Let me make a thick one. This guy right here, let's call it R. And then this guy right here, let's call it H. So please define what letters, what independent variables you're going to use here. Let R be this and H be this. And C will be the cost. Okay, so now how do you do this? Either top is going to be, the top is going to be, with the lateral surface here will cost what? This lateral surface, 2 cents. 2 cents per centimeter square. And then the top and the bottom, how much? It costs 4 cents. The top and the bottom are more expensive. 4 cents per centimeter square. Okay, now let's figure out the cost. What is the cost? Okay, let's see the cost here. The C is now the cost. It says here, find the cost is minimum. Cost is minimum. This cost will be our objective function. Everybody get this? Cost is our objective function. Why? It says here, such that the cost is minimum. We want the minimum cost. So we can see that cost is a minimum function. C will be our objective function. If you write the surface area, then that will be a mistake and that will be useless. Any questions up to this point? Okay, so now let's look at the C. What is the cost? The cost is, first of all, what is the area of the top? The area of the top is pi r squared. But then the top and the bottom have the same cost. So why don't we multiply this by 2 to show that top and the bottom? So the area of the top and the bottom is 2 pi r squared. And then what is this for here? Oh, that's the cost per unit. So if you look at that C is equal to 2 and then pi r squared, and then pi r squared, and then times 4. Let's look at the unit here. What is the unit? This is now 2 pi rh. You know, if the second term is this guy here. What is this? This guy is pi r squared. The unit is going to be centimeter squared. What is the unit of 4? Can you tell what the unit of 4 is? What is the unit of 4? What is the unit of 4? For what?
Cents.
For
Cents per centimeter square.
cents per what?
Centimeter square.
Per centimeter square. So if you multiply all these units here, what do you get?
Cents.
Multiply all the units, what do you get? This will be now cents. Times what? Here we have to multiply by 2. Same thing here. So this guy is R is centimeter, and then C is also centimeter, and then what is this 2 here? 2 is cents per centimeter square. So if you look at all the units here, then it will be cents. So make sure you think about the units, okay? So that's why a unit, and then the final unit will be dollars. You know what? Wrong. I should not be putting dollars here. I should be putting what? Cents. Okay, so cents. I should have put cents here, not dollars. Yeah, they're both the same unit, but I think because this cost is dollars, usually I put the dollars there. But the unit should actually be cents, not pesos, okay, not euros, but cents. Okay. We have many other money units as well, not just U.S. dollars, but anyway, in this case, U.S. cents. Just cents. Okay. And then now, what is this? Pi. And then what is the condition here? Now, if you look at this objective function here, we have 2 independent variables, R and H. R and H, we have 2 variables. So now we need to have one constraint, and the constraint will be this: pi r squared H is 125. Oh, the volume is 125, and we don't want to have any volume here. The setup is only going to consist of C and X and Y. The name of the objective function and the independent variables of X and Y. That's a mistake too. It's not X and Y. It should be what? It should be R and H. Yeah, you know what? When I was writing these notes here, I was watching my favorite soccer game. Sorry. I was writing these notes when I'm watching my favorite soccer game, and so I didn't pay attention. Okay, all right. So anyway, it should be R and H, and then that's it. And then if you look at the C now, I'll come back. Solve C. Okay, C equal to this. Now note that there's R and then there's H here. So what's the best thing to do? Let's just get rid of the H. How do you get rid of the H? H is equal to 125 over pi r squared. There we go. And then do all that, and then do the calculus dCdr, and then you get this. And then now, you know what, graphing chart. Now this guy here, you know what is this here? This guy is equal to, what? This is equal to R minus quarter of one, you know what, let me erase this part right here. Let me just erase this part. We don't need this part here. Let me just take out this part. The units, I guess we don't need it. I'm confused. I didn't say the screen, okay? I'm just reading this. And then, what is this part right here? This red box right here. Can you factor this? Yes, we can. This is going to be r minus, and then what? Cube root of 125 over 4 pi. And then what is this other guy here? Do you know anything about this other guy? Do you know anything about this other guy? This other factor? Do you know anything about this other factor here? What do you need to know about this other factor? Well, let me say this. A cubed minus b cubed is equal to what? Is equal to a minus b, and then times a squared, and then plus ab, and then plus b squared. And so let me now, let me spend a little bit of time here. This is yeah. So this what is this here? This is a cubed minus b cubed is equal to a minus b times a, and a minus b times a squared plus ab plus b squared. And all of you are tired of this, right? Because you have seen this guy so many times. So this is plus, and that's a plus, and this guy's a minus. The question is, what do we know about this guy right here? Do you know what we know about this guy? This guy's actually a squared plus ab and then plus b squared over 4. Why don't we complete the square? Complete the square in terms of with respect to the variable a. So we get this. You know what? One of the problems which was on section, I think it was section 3.1, was show x cubed is increasing. Do you remember that problem? I didn't do that. It was one of the common notes. Show that x cubed is increasing. So when you have to show that x cubed is increasing, this is the same thing you will get into this problem right here. And so if you look at this here, this is the same box right here, same value as this box right here. What is that equal to? That becomes a plus b over 2 squared, and then plus 3 over 4, and then plus 3 over 4 squared. So now, can you see what's going on here? What I'm trying to get at? What I'm trying to show you is that this guy right here is always what? Is always bigger than 0. So bigger equal to 0. This cannot be negative. It can only be bigger than 0. And by the way, equal to 0 only when what? Equal to 0, let me put a comma here. Equal to 0 when what? Equal to 0 when what? When a is with b equals 0. So that's the only time when that will actually equal to 0. So what we're trying to say is that this guy right here, note that in our case, b is not 0. B is not 0. It's b cubed is 125 over 4 pi. So all we know is that this guy right here, this guy right here is what? It is up. That's all we have to know. So you have to know this. Otherwise, you cannot analyze the sign of this guy. So when you have this guy here, this guy will always be a plus. What happens if you have minus here? If a minus is here, then you have minus right here. But other than that, everything is exactly the same. So the quadratic factor of a difference of square of cubes, difference of cubes of sum of cubes, will always be positive, okay? Anyway, the graphing chart, I'll let you do the graphing chart, and then you can finish that up. But anyway, I've basically done all the work for you, okay? You have to do the graphing chart, and then you have to write the answer. Okay, let me save it, let me clear it. Okay, so let's move on here. We don't have that much time here. Okay, let's look at example 5 first. Example 5. Find the point on the curve y plus x squared closest to point, 3, 0. What is this? Here we have a curve. Y equals x squared. This is y equals x squared. And everybody likes y equals x squared, right? Does everybody like y equals x squared? Yes. So we have the curve y equals x squared, which is our favorite curve, right? Yes. Okay, so now the question is what? Oh, so we have the point. Where's the point? Now we have the point here. Oh, now this point right here is 3, 0. 3. The point is 3, 0. We just put a mark 3 there. So now the question is, find the point on the curve y equals x squared close to the point 3, 0. So there's a point here, P somewhere. P somewhere here. And we want this to be the minimum. Oh, that's what it is. What is the minimum distance? That's what it is. The question is to, what, minimize the distance. Can you minimize the distance here? That's the question. Get it? Does everybody understand the question? So we want to let this point, let x be a point on the curve this. So this one, oh, let's use sign in. Let me just call this guy P. I should have called this guy point P here. But anyway, x, be a point on the curve y equals x squared. And this x, y will be consistent with this y, or this x, y here. So there will be no problem here. So we can call that point x, y. In this case, we can. If you're not sure, then call this guy a, a squared. That's what you should call it, okay? So don't call it x, y if you're not sure. So now in this case, setup. Now let's get the setup. Setup is the distance between what? X, y, and 3, 0. I should have put a parenthesis here. I guess I forgot to put a parenthesis there. The distance between the point x and y and 3, 0, and that is this guy right here. Now the distance is the objective function. Now it says closest here. So what's the function? What's the objective function? Objective function is the distance, because we want to find the closest point of the objective function. Objective function is equal to the distance. In this case, the name of the objective function is not written here, but you have to kind of get it from the meaning of this problem. The word closest means minimum distance. Again, closest, min distance. That's what it means, right? So minimum distance, that's what it means. Okay, so that. And so now this distance is this. And then what is the relation between x and y? Well, y equals x squared, and then find min d. So min d, who's min d? Who is min d? Min d, this is your girlfriend, right? What is min d? This is your girlfriend, min d. Okay? Okay, so now solve how to do this. Equal this, good. But now the first step is we have two variables x and y here. So why don't we first, eliminate one variable. So in this case, what I did was I substituted y equals x squared. So I substitute this guy here. So the setup is this. The y equals x squared. So you replace y equals x squared, you get this. And then you get this right here. And so what we do, we take the derivative. So when you take the derivative, this is what you get. And so you simplify this, you get this. But now the question is, we have to analyze the sign. So now the question is, what is this guy right here? How do you factor this guy? Can you factor this guy here? Factor this. How about, let's call this g of x is equal to 2x cubed, and then what, plus x, then minus 3. Oh, we have this function right here. So what is the easy way to factor this guy here, class? Can you factor this? We have studied this somewhere. When did we study this? Factor. Note that in this case, we cannot use the quadratic formula. So what do? Now we use what? Apply two-factor. So two-factor, what do we do? Apply rational zero theorem. Rational zero theorem. And what? Rational zero theorem and what? What is the other theorem? A factor theorem. Apply factor theorem. Rational zero theorem. Do all of you remember these two theorems here? The rational zero theorem and factor theorem. Do you remember this? You know when we studied this in our class? We studied this 22 years ago. We studied these theorems. How many years ago? 22 years ago. Okay, all right? Remember this guy? So what do we plug in here? How about this? How about try x equals 1? And what is G of 1? G of 1 is equal to what? 2 plus 1, and then minus 3 equal to what? 0. Oh, great. Look at that. Oops. I have no space to put the exclamation mark there. So we get this. Oh, this. 0. So now I left the blanks there. So what is it? What should go in the blank? So that means G of 1 equals 0. That means what? That means we now have this. This must be x minus 1. And then once this guy is x minus 1, then what's the other guy? And you do this. How do you get the other guy? Synthetic division. Synthetic division will do. So do you all think that synthetic division was over by now in chapter 3? No, it's not over. These guys pop up. 1, 2, 2, 2, 2, 3, and then 3, and then 0. Oh, look at that. So this guy is now 2x squared plus 2x, and then plus 3. Now, we have to factor this guy further because we have to analyze the sign, right? So this guy right here, what is this? Can you factor this guy? This guy actually happens to be positive all the time. How do you show that that's positive? Well, you show this by completing square. Completing square. Completing square shows up again, okay? All right, anyway, and then I'll let you do the rest, okay? So basically, at x equals 1, we get the minimum right there, okay? So class, well, I'm a little bit short of time. I think let's now move on to example 6. Example 6, okay? Example 6 here, find the maximum area. You know what, I forgot the most important word here. What word did I forget in the question? Can you tell me? Can somebody tell me what I forgot? Semicircle is the picture is this right here. The semicircle is this. So let me put it up a little bit. So let's look at this. Semicircle is right here. What is the important word which I forgot on the question? Can somebody tell me what word I forgot on the question? Stop. Somebody tell me what I forgot. Find the maximum and then what? Oh, I forgot here. Oh, what did I forget? Maximum perimeter? Maximum what?
It's the area.
Right, the area. That's the. I forgot the objective function. Okay, so my mistake. Obviously, I told you already. I was watching my favorite soccer game and eating my favorite burrito, and so when I am watching soccer and eating my burrito, that I cannot pay attention, right? So that's what was happening here. Anyway, find the maximum area. Okay, so now we have this. Okay, now it's this right here. Okay, so now we will inscribe a rectangle. A rectangle is going to look like this. The rectangle is going to look like this. And then the radius of the circle is r. This guy's r. Let me call this guy r. Okay, this is again the radius of the circle is r. Radius r. So this guy right here is r. Okay, now this example 6 is kind of interesting because there are actually two setups. One is the standard setup, and the other one is the biangle variable. So you know what? The standard setup is this. Call this guy this point. So why don't we create a xy axis here? This xy axis is possible, not possible. How about this? Let me just erase this. Let me not put a reference of xy axis here. You may want that xy axis, or you may not. So that's not mandatory. So now how about this? Why don't we now call this guy x? So in this way, there's no reference of xy axis, and this y, and then let me call this guy y. Y will be the height of this guy. Okay? If we do that, then what is now the area? Area is xy. And then area x and x is bigger than 0, y is bigger than 0. Actually, what is true is that x is actually what? Between 0 and r. And y is also between 0 and r. Okay? And so now what you do is you have this right here, and then what? And then we have all this. Maximum area is this, and then the area is actually this right here, and then you do all that, and then you can do the graphing chart. Not a problem. Okay? The rest of it, you have to do this, and then you can do the graphing chart. Now, let me now discuss the solution 2, setup. This is the interesting one. In this case, what I'm going to do is this. I'm not going to do this here. I'm going to do this here. I'm going to draw a semicircle, and then put this here. And then this is r. And then the rectangle is like this. You know, in the solution 2, this is not solution 2. In solution 2 setup, we are not going to create x and y. You know what we are going to create? We are going to draw a rectangle. We're going to draw a line there, and then that will be the corner of the rectangle like this. And I'm going to create a theta here. So let's create the angle theta. So I'm going to create the theta there. So this one, let me create this angle theta. Oops. Black. Let me call this guy theta. So if you just put a theta here, and that's the center of the triangle, and this guy, so what we have is this. We have r here, and this guy is theta. So in setup in solution 2, the variable I'm going to create will be theta, and only one variable. There's no x and y. In that case, what happens is this guy right here, this is r cosine theta, and this is a right angle, and this is r sine theta. So in this case, what is the area going to be? Area, you know what the area is going to be? Area is going to be this. Area is going to be, what is going to be 2 times r, 2 times r cosine theta. Cosine theta, you know what? I cannot theta. Let me just put theta. Okay, let me just put theta later. And the times what height is what r, and then sine theta. You get this. So the area will actually be this right here. And you know what? If you have to apply the double angle formula, you know what this becomes? This by the theta, only one independent variable, no condition. So this will actually be r squared times what? 2 cosine theta sine theta, that's sine 2 theta. Oh, you know what? This if you set up this way, we don't even need calculus. Calculus not needed here. Calculus is not needed. Why? Because in this case, max area is equal to area equal to what? Is equal to r squared. And that is the area when, say, when theta is equal to pi over 2. Let me write this down. R squared. Because we know the maximum value of sine theta. Sine theta, sorry, it's not sine theta, sine 2 theta. What am I saying here? Oops. Sine 2 theta. What is the maximum area? The maximum area is R squared. Because we know that this guy maximum is 1. Sine of anything maximum is 1. And the area, when theta is equal to what? When theta is equal to, when this guy is 90 degrees. We know that sine 90 is max is 1. That's maximum. So R must be what? Theta must be pi over 4. The solution 2 is amazingly simple. We don't even need calculus. Oh, I got no calculus needed here. No calculus. Calculus not needed. Not needed. Which is a good thing. And when you don't need calculus, what is it good? Very good. That's very good. Calculus is not needed. We don't need calculus. It's a very good solution. In fact, I think solution 2 is the superior solution than solution 1. Look at solution 1. Do you see how messy it is? Whereas solution 2 is so simple, no calculus, much easier. Because now, I ran out of time here, so I cannot do anything. But however, the rest of the section will be covered. So just give me a few minutes here. Oh, let me see. Just give me a few minutes. Then I will try to wrap it up. And so let me clear all the drawings here. And so now what I'll do is this. If you look at example 7 and 8, we now have these questions here. Find the maximum volume of the cylinder inscribed in a cone of radius r and h. And here I have given you all the setup here. So please study these guys here. Okay, these guys here, I want you to study. And if you have questions before the class, I will go over this. But the setup is this right here. So again, the setup is there. I want you to study. This is all covered. This is a maximizing volume of a cylinder inscribed in a cone. So basically, you have a cone. So let me just draw the pictures. I think I'm going 2 minutes overboard here. You have a cone here. And then what? And then what are we doing here? Maximum volume. Oh, yeah. You're inscribing a cylinder. So let me draw this in red. You're inscribing a cylinder. So we want to maximize, you to find the maximum volume of the cylinder. So we want that volume here. And the cylinder is fixed. Because cone is fixed. Cylinder, we want to find the maximum, cylinder maximum volume. Now, if you look at the example 8, this one now is inscribed in a sphere. Now we have a sphere. In example 8, we have a sphere. And so let me do this here. We have a sphere. Let me draw this in red, in black. So this is sphere. We have a sphere here, right? We have a sphere. And now, what is the problem in example 8? Find the maximum volume of a cone, okay? This cone, or what I mean by a cone is, of course, a right circular cone. The technical name is right circular cone. We are not going to contain any other circular cone. That's the cone we know, the best cone, the right circular cone, and that cone will be inscribed in a way like this. It will be inscribed like this here. It will be inscribed here. Oh, let me write this in red. Draw this in red. So we now have this here. This here. And then we want to create a cone like this. So yeah, we want to. So now the question is, how can you maximize the volume of a cone? That's example 8. Okay. So that's just, let me save all this and clear all this. Now, if you look at example 9, I didn't do anything here, but if this one is now a sphere and not inscribed a cylinder. Very similar kind, okay? But anyway, I just have to stop here. All of this is covered. Okay? So once again, tomorrow we have a test after class, regular meeting, and then after class, I'll give you at least a 9-hour window to take midterm 3. And midterm 3 will cover everything up to what we have covered so far, including example 7 and 9. They're all covered, okay? Okay, all of you have a good day, and I will meet you tomorrow morning at 8. And the test, you have to take the test after the class is over. Okay, bye everyone.
You said we should expect another test before the final sometime next week, right?
So tomorrow we have midterm 3, and then I think probably next week Monday we'll try to have midterm 4.
Got it.
And then 3 days later, which is the Thursday, we have finals. Okay, I know it's very tight, but 6-week class, it's always like this. I mean, there's no choice. Okay, so I mean this is the good thing about a 6-week class. Don't you like it? You have so many tests, right? In a short time.
It's great.
Yeah, great. It's a great way to finish a course, right? This is a great way to finish a course, if you can handle it, of course.
Thank you, Professor.
I'll be here to answer any of your questions, any housekeeping questions or any math questions. If you have any questions, yes, I'm here.
Yeah, Professor, sorry. Could I ask you a question?
Sure, what is the question?
So on section 3.4, if you ask us to, prove like a vertical asymptote using limits, for vertical asymptote, like let's say, like going back to like the first example where the vertical asymptote x equals 1, and when we solve by limits, do you want us to solve it both from the left, like one approaching from the left and the right side, or
no,
just
if one of them, for the limit statement, if one of them is true, then that's the conclusion that is a. So all you have to show is that that asymptote is a one-sided asymptote. So you don't have to show me it's a two-sided asymptote. Okay. It's a one-sided asymptote, that's fine. So you just pick one of them. You know what? If you're not sure, then let's say let me just write it here. Example. We have an example. So let me write it down. So let's say y is equal to what? Y equals f of x, and then I show that x equals 1 is an asymptote. Is a vertical asymptote. Is an or a or anyone vertical asymptote. You don't have to show me that that's a vertical asymptote. The equation will show. So let's say if the question is this, let's say for somehow let's say you find that x, for example, and basically what you have to show is this. You have to show that. Then what you have to show the mathematical form, change it. That means you have to show that the limit of f of x, to show that the limit of f of x is equal to, and then you have to show that this guy is infinity. To show this, x approaching 1 plus is equal to infinity, or plus or minus infinity, plus or minus, or minus infinity. So how do you show? The way you show this, you start with this limit here. Don't just write it says 0 infinity, but you have to write f of x, and then x is approaching 1 plus. And what do? You actually evaluate this. You evaluate this limit, and hopefully this limit will become infinity or minus infinity. You have to evaluate this, not just write infinity or minus infinity, but you have to evaluate. You have to actually solve, get the value of this limit.
I understand.
Get that? So that's how we show it.
Yeah.
They show that the limit is, let's say, y equals 2. So how do you show that the let's say what is this here? Let's say show that the asymptote is y equals 2. Then what you have to show is an asymptote. Then you have to show that what? Show that the limit of what? Limit of f of x, and then at x goes to infinity. So now you just try f is approaching infinity, and then and now this is the right side, and then hopefully this will be 2. Is 2? Is this correct? If not, then you have to try x approaching minus infinity. They can literally be different. If one of them becomes 2, then that means y equals 2 is an asymptote. So you have to either show this or this, but you don't have to show both. Just one of them is fine. So this is the way to show that. For example, show that y equals f of x, the f of x as asymptote y equals 2. If I ask to show it or prove it or verify it, if I use a strong verb there, strong verb, then that means you have to actually show this guy. And that means you don't just write this down, but you evaluate this limit. Must evaluate the limit. That means you have to calculate. Evaluate the limit. And you must show that that actually equals 2. Don't just say it's 2. You have to evaluate that and then show that that is actually